Okay, this is part 2 of Unit 10B, and now we're going to be looking at angular size and distance. So, imagine if you hold a coin in front of one eye, it can block your entire field of view, but as you move it further and further away, it appears to get smaller and it blocks less of your view. So the true size of that coin doesn't change. Instead, what changes is its angular size, the angle that it covers as seen from your eye. So here's this little figure down here. You can see here's your eye. And as you slide this thing away, things are going to change. So this figure shows the effect. So imagine that you've got a vertical circle all the way around your eye, with the radius equal to the distance from your eye to the coin. So notice that because the coin's angular size is small, the physical size, or the diameter, is approximately equal to the arc length of the small piece of the circle that it subtends. So hopefully this little drawing here makes sense. Here's your coin. Here's an object that's behind it. This distance is going to be your radius here. Is those little lines you're drawing, or you're seeing some figure behind it, or behind this coin. So another way to put this is the ratio that the coin's angular size to the full 360-degree circle is approximately equal to the ratio of its physical size to the circle's circumference, which is 2 pi times the distance. So here is generally what we're getting at, is the angular size over 360 degrees is equal to the physical size divided by 2 pi times the distance. So you don't need to know all the derivation and exactly how all that geometry comes about, just that relationship there. And what we can do is we can use this to estimate sizes of particular objects. So again, here's kind of a formal small angle formula for angular size, physical size, and distance. So the further an object is located from you, the smaller where it will appear to you, and that angular size depends on the distance from you. So as long as an object's angular size is less than a few degrees, the following formula relates its angular size, physical size, and distance. So again, these are usually things that, again, those angular sizes are very small in degrees. And this is where getting down to degrees, minutes, and seconds can be helpful because we're dealing with small angles. But then the angular size is the physical size times 360 divided by 2 pi times the distance. And another thing that would be helpful is if you solve this thing for the physical size, you would just divide by, well, I'll just say times by the reciprocal of that thing. So you times by 2 pi times the distance over 360, 2 pi times the distance, over 360, and those would cancel, and that would be the physical size. So you can go both ways here. So in this example, number 39, we have the sun has an angular diameter of about 0.5 degrees viewed from the Earth, and the distance from the Earth is about 150 million kilometers. What's the true diameter of the sun? So in this case, we want to know, what is that physical size of the sun. So the physical size can be found by the angular size times it by 2 pi times the distance, all divided by 360 degrees. So the angular here is 0.5 or 0.5 degrees. Then we times that by 2 pi times the distance, which is 150 million. So I'm going to say 150 times 10 to the 6th for millions there. And then divide by 360 degrees. So you can see your degrees are going to cancel. So when I multiply all this out in my calculator, I get roughly 131 million. It's like 130,900 something thousand, but I'm going to round it to three significant digits. So 131 million, or 1.31 times 10 to the 6th. And this is in kilometers. So that's a rough way to estimate the diameter of the sun when you're here on the Earth. Okay, but again, hopefully you can see how knowing it, in this case we use it very general, half a degree, but if you were to get into something that had degrees out to the 4th and 5th decimal place, rounding wouldn't be helpful there, but using degrees, minutes, and seconds would be helpful, and having a tool that could give that to you as well. Next thing we're going to talk about, so we're going to kind of switch from angles now to some triangle applications. And this is pitch, grade, and slope, something that you see a lot when you're driving on the road. They'll give you they'll tell you a degree or a grade or a slope or something of the road ahead. So, if we look at a road that rises uniformly 2 feet in the vertical direction for every 20 feet in the horizontal, okay, so again, vertically 2 for every 20 feet. Okay, that road makes an angle with the horizontal that we can measure in degrees. So it makes some angle here. However, it's more common to say that the road actually has a pitch of 2 and 20, or that can be reduced down to 1 and 10. It's also common to describe the rise of the road in terms of a slope, which we talked about in the past. In this case, the slope is rise over run, which is 2 over 20, or 0.1. And if we express the slope as a percentage, that's what we use the grade, and the grade is usually what you'll see when you're driving down the road. And the grade of this road is 0.1, or 10%. That's a pretty steep grade right there. If you're driving on the freeway or something like that, that's a pretty steep grade. But this idea of slope or pitch or grade. It's a way we determine how much we're rising over a certain horizontal distance, or how much we're falling over a horizontal distance. So if we have a sidewalk that's got a pitch of 1 and 6, or we've got a sidewalk of a pitch of 15 degrees in grade, which one is steeper? Well, we're going to take that pitch 1 and 6, which is 0.16 repeated, or approximately 0.17. And 0.17 as a percentage is 17%. 17% is greater than 15%. So a road with a pitch of 1 and 6 is steeper. Oh, man, I keep reading letters here. Is steeper than a 15% grade road. So, that's where we can use some geometry to determine steepness of roads, or we also talk about pitches and roofs and those things. And that's just one way to determine which is steeper, and how we can kind of relate the two when we talk about pitch or slope or grade. We bring them all together. When we're looking at triangles, especially right triangles, the Pythagorean Theorem, which only applies to right triangles, those that have a 90-degree angle. But this thing can be used very frequently, and hopefully is something that's in your brain. A squared plus b squared equals c squared, where c is the longest side of the triangle. It's opposite the right angle. We call that the hypotenuse. And just check myself for time here. Yeah, we got time to do this. So let's suppose that you've got this very generic map over here, and when we're going north and south, each block is 1/5 of a mile. For going east and west, those blocks are 1/8 of a mile. We want to find the shortest possible walking distance where you have to follow the streets, and we are going to be going from the theater to the library. So here's our theater. So if we come across on our theater, we're going to go 1, 2, 3, 4, 5, 6, 7, and then we'd have to go 8 actually, because it's on this corner. So we'd have to go 8 blocks. That would be going east. And then you'd have to go down 1, 2 blocks south. Okay, we need to find out what is the distance there if you had to walk. From the theater to down to the library. So if I go 8 blocks east, that would be 8. Every block east is 1/8 of a mile. Then plus 2 blocks south, and each of those is 1/5 of a mile. So that'd be 8/8 of a mile plus 2/5 of a mile. 8/8 is 1. 2/5 is 0.4 or 41/100ths or 4/10. So this is 1.4 miles that you would have to walk. And that's the shortest possible distance to go in 2 straight lines, because you wouldn't want to take some you can try and see if some zigzag pattern is going to get you there, but it's going to be shorter to just take straight one way and then straight the other way. So that's part A. Now part B, find a straight line distance as the crow flies between the 2 locations. So this is going straight from the theater to the library, and we're going to find out the distance there, and we can assume that this is a 90-degree angle where we turn from going exactly east to going exactly south. So then I'll just call that distance D. We would have D squared equals, and it was 1 mile going west, so 1 squared plus, and it was 2/5 of a mile going south, so 2/5 squared. So then you'd say distance squared, well, I'm just going to square root both sides right there. So distance is going to equal, we don't need to do plus or minus in this case, because distance being negative doesn't make sense. So 1 squared plus 2/5 squared, and 1 squared is 1 plus 2/5 squared, that'd be 4/25. And this would be, if I get a common denominator, that would be 25/25 plus 4/25, which is 29/25 square root there. Or you get it down to 29, square root of 29/5. But, if we take that to a decimal and we take it out a couple of decimal places here, let me see what I got. I got 1.08 miles. So that would be the straight line distance if you were able to fly. And that's one of the reasons why flying is faster than driving or walking or whatever the case may be, because we have restrictions on the ground where we can't just plow through people's neighborhoods when we're walking or driving. But flying, you can go straight there. So yes, flying, you do go faster as far as speed usually, but the straight line distance is what helps cut off a lot of time as well. So that's a look at some more geometry and the Pythagorean Theorem. If you have any questions, don't hesitate to let me know, and we'll finish this up in part 3.